Hello everyone. Today I'll be presenting our project, Portable Piezoelectric Flag for Wind Energy Harvesting. The team members of this project are Sharif Ismail, Yaqub Suleiman, Muhammad Hamid, Nasser Taifour, and I am the presenter Muhammad Barakji. This project was supervised and advised upon by Dr. Mehdi Omem. There are many types of energy harvesters, but our main focus will be piezoelectric energy harvesting. Energy harvesting using piezoelectric transduction lies on vibration of structures. The process by which piezoelectric wind energy harvesting works is simple. It begins with external excitation, which will happen through wind. This external excitation will cause mechanical vibration, which will turn into electrical energy through the piezoelectric material, and thus giving us a power output. Our main goal is pursuing the optimization of the clean and renewable harvested wind energy. The problem that we are trying to fix is that mechanical energy such as wind flow exists widely in the nature as a renewable and sustainable energy source. Such energy can be utilized in rural or deserted areas where access to conventional power sources is restricted. Therefore, a small-scale wind power generation solution is needed. The solution must be portable and easily deployable in large quantities in areas with limited accessibility. Furthermore, the solution should be self-sustained as regular maintenance is difficult to carry out in deserted regions. Our objective is to create an innovative, portable, fully integrated system of a highly flexible piezoelectric structure to harvest and store wind energy. This piezoelectric system will utilize microfiber composites that can serve for low-power applications. The project was conducted in four main phases: research, modeling and simulation, prototyping and testing. Our solution utilizes the best features of the three previously mentioned potential solutions. Our design utilizes a piezoelectric energy harvester, which uses an MFC strip in a vertical configuration, and attached to the MFC strip is a triangular leaf. The MFC strip is placed on an aluminum substrate, which is attached to an aluminum leaf using a nylon hinge. The MFC strip is connected to a voltage conditioner, and the electric output is stored in a power bank. The advantages of our solution is that it has excellent flexibility on large deformation and reliability in electronic devices. Also, it offers high power generation, thus making it the perfect choice for an energy harvesting system. This advantage of our system is that it is a bit more expensive and has a lower fatigue life. Now, I will explain the reasons behind our solution. First, let's begin with the configuration of the flag. We chose a vertical configuration over a horizontal one, as according to our research, a vertical configuration can produce up to double the amount of power in comparison to a horizontal configuration at the same wind speed. As to why we chose a triangular leaf instead of any other geometry, a research paper showed that a triangular shaped leaf with a base and height each 8 centimeters helped in providing the maximum power output in comparison to any other geometry such as a square or a rhombus. As to why we chose to include a leaf in our system, a research paper conducted two tests, a flag that is attached to a leaf and a flag that isn't. As you can see from the graph, the displacement of the flag with the leaf is approximately more than double than the displacement of the flag without the leaf. So we can conclude that the leaf acts as a vibration amplifier, which increases the strains on the piezoelectric material and leads to a higher electrical output. Our system consists of four main components, which are the substrate, isosceles triangular leaf, MFC strips, and a hinge. According to the two figures, the average wind speed around the UAE floats around 4 meters per second, and that will be the critical flutter velocity that we will need to target. Now that we decided on our design, its components, and the materials that will be used, we can begin our testing phase. The parameters that affect the flutter speed are the length of the substrate, thickness of the substrate, material used for the substrate, and the bluff body effect. This is the experimental setup that allowed us to reach to our final design. The experimental setup consists of a flag, a displacement laser sensor, movable bluff body apparatus, an anemometer, and an oscilloscope. Our experiment begins with the wind generated by the wind tunnel, and the speed of the wind is recorded using an anemometer which is connected to a LabQuest Mini and connected to a computer. The wind induces mechanical excitation on the flag, and the displacement of the flag is measured by a displacement laser sensor powered by a power supply. The laser sensor is connected to an oscilloscope, which is then connected to the computer to store the data for later analysis. The flag is also connected to an energy harvesting circuit, which is connected to a multimeter to record the voltage and current output. Our first test uses a galvanized steel flag without a bluff body, and it has the following dimensions: 140 millimeters high, 20 millimeters wide, and 45.45 millimeters thick. Our experiment concluded that we could not reach the flutter speed of the flag Our second test uses an aluminum flag without a body. The flag has the same dimensions as the galvanized steel. In this test, we concluded that the flutter velocity of this flag is about 10.5 meters per second. Our third test also uses an aluminum flag without a bluff body. However, dimensions are now 200 millimeters in height, 20 millimeters in width, and 45 millimeters in thickness. From this test, we can conclude that the flutter velocity of this flag is 8 meters per second. From the 3 tests conducted, we can conclude that the aluminum flag with the dimensions 200 by 20 by 0.45 millimeters will give us the best chance at achieving the lowest critical flutter speed possible. This critical flutter velocity will be further reduced when we attached a bluff body to the flag. Now that we have chosen our flag, which is the aluminum flag with the dimensions 200 by 20 by 0.45 millimeters, I will explain the effect of attaching the bluff body to it. The bluff body will further increase the displacement of the flag and lower the flutter velocity. The video on the left shows how the bluff body creates vortex-induced vibrations, and the graph on the right shows how attaching the bluff body more than doubles the displacement of the flag, assuming 170 millimeters to be the zero position. The graph on the right represents the effect of the bluff body on the flag of choice. In this test, we used our flag of choice, and we attached a bluff body to it. From this test, we can conclude that the flutter velocity of the flag with the bluff body is around 5.7 meters per second. This table summarizes all the results of using different flag dimensions, different flag material, different bluff body sizes, and different bluff body distances. What we can conclude from our test is the following. Increasing the length decreases the flutter speed. Decreasing the thickness decreases the flutter speed. Decreasing the modulus decreases the flutter speed. Adding the bluff body decreases the flutter speed. Changing the bluff body distance between 15 and 25 centimeters had a very small effect on the flutter speed. And our final chosen flag is an aluminum flag with the dimensions 200 millimeters in height, 20 millimeters wide, 0.45 millimeters thick, and it's attached to a bluff body, which results in a flutter velocity of 5.7 meters per second. Our final product design consists of an aerodynamic elliptical shaped body with a USB port and LED indicator to show that there is an electrical output. The flag will be held in place by a slider. The advantages of our final design is that it is user-friendly, no screw holes in the substrate are needed. The freedom of movement of the slider gives freedom to change the substrate when needed, minimizes the drag from wind flow, and has an adjustable bluff body position. However, the elliptical shaped body is difficult to 3D print. The result of our final product, we can produce 5 volts at 45 milliamps leading to a power output of 225 milliwatts. Thus, we were able to charge a lithium polymer battery, and the expected charge time of a 200 milliamp hour battery is approximately 12 hours.